Mhm. Okay. All right, let's continue the studying the spin. 1 second. Okay. Sorry, something's wrong with me. Okay, I think it's okay now. All right, let's continue. So I gave you a brief explanation of the spin, right? And let's continue. So we will learn today how to describe it mathematically. To start, we will first review magnetic dipole moment. The classical concept will first cover it here. So if you have learned already, let's just review it. But if you're learning it for the first time still, I think it's okay because it's not that difficult. Magnetic dipole moment is basically a current loop. And then for convenience, I'll assume that it's a circle with a radius r. And this loop's direction, okay? This loop's direction, right-hand rule. So let me just do this. Right-hand rule, right? So vector is pointing up this way, and then I will call that magnetic dipole moment vector, right? Mu vector. And then this mu vector, since it's a vector, it's going to have an amplitude as well. That amplitude, you can call it IA, okay? IA is an amplitude, A is an area. The current times the area is magnetic dipole moment. If I take out the normal vector separately, I can do this unit vector based unit vector. This is a unit vector. The direction of this direction is defined by right-hand rule. So for those of you who have not learned classical electromagnetics, let me just briefly explain why this is important. Whenever you think about some magnetic material, right, something like magnet, you can model it as a collection of these stuff, okay? And then depending on how these things are oriented, you can have different properties of magnetic material. All right, so basically magnetic dipole, electric dipole, they are important in many senses, but when it comes to the material study, electrical material, right, its a permittivity or refractive index is all boils down to what kind of electric dipole you have at like each point inside a solid, right? So similarly, for magnetic material, it's a matter of how much of these are inside your solid state material, okay? That determines its magnetic property. So it's a basic building block of electrical or magnetic material, basic building block. All right, and then let's continue. So what we're interested in is this is a current, right? So current, you can think of it as some charged particle is circling around. So for a charged particle, remember this, angular momentum is linearly proportional to magnetic dipole moment. Okay, so this thing is like you have a basically I introduced the current loop, right? Actually, you can think of it as a charged particle circling around. So these charged particles will have angular momentum, right? Just circling around. So let's see how you can actually mathematically show this. It's quite simple, straightforward proof. What I'm going to use is that I'm assuming that loop, right? Loop is a kind of a, one second. It's a line full of charges, all right? And then it has line charge density, okay? Line charge density of rho L. And then that line is circling around. That's how I model this. It's a classical continuous way of modeling it. And then we think about a segment of length L, delta L, typical thought process in physics. After some time t, you will have this again. Okay, let's say it's moving towards the right-hand side. And then after some time delta t, this segment has moved here, and the segment has shifted towards the right. And then its segment length is still delta L. And then, so what I'm going to do is I'm going to make a link between this picture and the current I used up there. Okay, so whenever you measure current I, what do you need? You need a cross section, okay? You have some like defined cross section, hypothetical cross section, and then you just count number of charges passing through it, right? So I'm going to monitor here. So I'm going to monitor here and then calculate I, okay, measure I. And then this line is, the loop has a line charge density. And then let me make a link between them. So I is by definition how much charge, okay, in terms of Coulomb has passed through for a given time, okay, unit time. That's a current. And then how much is delta Q here? It's a total amount of charge, right? Total amount charge, you need to multiply line charge density times the length, okay? And then the one we're observing is that that segment has passed through from, when you're standing there at the monitor point, the delta L segment has passed. So delta Q is going to be rho L delta L, right? The total charge passed through. And then that's going to be divided by delta T. So that's current I, rho L, all right? And then the delta L over delta V, if you can actually think of it as a V, right? At the speed of that line moving. So let me call that V. And then if you assume that the line is distributed over that loop uniformly, then you can actually express rho L in terms of total charge divided by its length, 2 pi r. Okay. So, okay, we have a relationship between I, Q, and V. So let me use that to make a connection to angular momentum, all right? Because we already know like magnetic dipole moment, what we need to know is the angular momentum of this thing. So angular momentum, so let me just calculate the magnitude of it by taking the absolute value with R cross P, right? So R cross P, and then this R will be there, and then P is the momentum, so it's this, right? So mass is the total mass of that loop. So simply speaking, it's just the magnitude, it's just RMV. Everything is uniform across the loop. And then mu equals IA. I'm just calculating its amplitude, make things simple. So I, we have discovered there, right? Q over 2 pi RV. Let me write it this way. Okay, that's I. And A is what? I'm assuming circle, 2 pi R square, right? And then if you cancel out these pi's, and you can write it as 2 VR, but I'm going to add M here, okay, M. Okay, then what happens is that Q over 2ML. All right, we found that the proportionality constant between L, angular momentum, and mu, magnetic dipole moment. Okay, they're linearly proportional to each other for this simple model. Okay, let's move on. So this ratio, right, of mu over L is Q over 2M. This is the proportionality constant, right, between that mu and L. The proportionality constant. So this constant itself, right, no dependence on R or V. All right, it only depends on Q over 2M. So their ratio is not a function of R or V. Okay, that's the one observation we can make. It only depends on charge and mass. So it's called the gyromagnetic ratio. Right? Yeah, some circle that the current loop is working, and then it will make the magnetic dipole moment. The ratio between that is called the gyromagnetic ratio. All right, this concept will be extended and applied to spin as well soon. So let me go back to a Stern-Gerlach experiment and then discuss in the context of the spin, okay? Which picture, okay. So this picture I have shown you through the slide already. So it's a Stern-Gerlach experiment. So it used the silver atom. So silver is known to have 47 electrons. And then this is, you probably have learned this, how to fill the electrons to the orbitals back in high school. One S squared, two S2, two P6, three S2, three P6, four S2, three D10, four P 5s1 for d10. And then the outermost electron is this one, 5s1. So this is electron in charge of, let's see, okay. So let me show you another picture, which is showing how it is filled up with an energy level. It's this one, how silver electron configuration is made here. And then, right, so that 5s1 is the one that's making this Stern-Gell experiment working. Okay, it's like a magnet. Other things are all paired up, so they don't really produce magnetic dipole moment. So, as I mentioned earlier, the original Stern-Gell experiment, their interpretation was wrong, right? They said, one second, these two people interpreted as electron as orbital angular momentum. Okay, that's what? That's wrong. Turned out to be wrong. Because that 5s1 orbiter, if you really later analyze, right, it's not like really circling around. Okay, it's an s orbital, symmetric. It doesn't have angular momentum. It's zero, basically. So it's not responsible for making that magnetic effect. So after a lot of research, Pauli figured out the electron has a spin, okay, spin angular momentum. As I mentioned, it's just a metaphor, okay, not really spinning. But we use this metaphor because it's kind of giving you a mind picture of how the magnetic dipole moment is being made. So that is correct. Turned out to be correct. It explains all the physics in detail very well. Right. So let's continue. In classical picture, total Q over 2m was the gyromagnetic ratio. So for electron, this one, so instead of L, I'm using S to represent the spin angular momentum, okay? I just changed it from L to S here. In classical picture, this is the equation we just derived together, okay? We just derived together in this previous slide, right? Q over 2m. So I'm rewriting it with replacing L with the S. So turns out that you actually need to update this, okay? Update this by accounting for relativistic effect. Good. Dirac made this contribution, okay? He made this correction, and then you actually need to write this way. You have to multiply the correction factor G in front of everything. And then this is called the G factor. And for free electron, the G is 2, okay? For electron. So the G factor can change for specific systems, but roughly they are almost 2. And then mu E is roughly 2, so I'm just using 2. And then so I want to rearrange our equation in the following way. So this is what we have found so far. And then what I'm going to do is that I'm going to add h bar here, like this. Okay, and then let's look at the unit of S and H. Unit of S is angular momentum, right? Angular momentum. So it's what is it? If you think about it, it's RMV, right? R is a radius, it's a length. M is a mass. V is a meter per sec. That's a unit. If I rearrange it, kilogram, meter square, second inverse, that's a unit. And then Planck constant, unit is known to be joule times as a second. Joule is the work, right? Work is what is the F equals ma, and then you multiply the length. So you have this, okay. So it turns out that kilogram, meter second, mass one. So what did you see? Their unit is the same, okay? Unit is the same. Actually, h bar has a unit of angular momentum. So this one is unitless. All right, so unitless. And then, given this observation, right, it is actually nice to define this thing called the mu b. It's defined as this. Bohr magneton. All right. So to wrap this up, mu e to mu b s over h bar. And then the spin angular momentum s, actually you can assign some vector direction. Since it's a negative charge, there is a negative sign, and you can write it this way. All right, the Bohr magneton is quite important because the constant actually giving you the kind of basic like magnitude of a single electron. And then usually S, right? S over H bar, the number is on the order of 1, okay? Can be half or 1 or whatever. So Bohr magneton is giving you how big it is, the single electron, its magnetic field. All right, so that was enough about magnetic dipole moment of electron spin, how you quantitatively handle it. Let's move on to the details of a Stern-Gerlach experiment. So here I'll describe the physical mechanism of a Stern-Gerlach experiment, which is not super difficult. Basically, you can think of everything in terms of sort of the classical like current loop picture. So what I'm going to show you is you have what did I say? You need to have this gradient of the magnetic field, right? Gradient magnetic field, B field along Z direction. So as you go up, so I'm showing you its magnitude getting larger. It's stronger up there, and then there is this current loop. current loop I is flowing in here, and then we want to focus on this part, okay? So we will just to carry out simple calculation here and here, and then the current direction is on the right hand side is going into the plane, on the left hand side is going out of the plane, right? You can see that. And then for those things, let's just calculate the direction of the the force, okay? The current is going out of the plane, and then what is that? Your B field is pointing in this direction for the left side, right? So you can use this rule, right-hand rule, to calculate its force, right? So then you can, if you calculate, I is like going out and B is this way, you use right hand, and then you will see that the force for this small segment is going to be this one. Okay, it's the left up is the force direction. And then you can do the same thing for current going into the plane. It's all high school physics, so not really difficult. This time, you can see that on the right-hand side, the B field is left, pointing left up, right? This is B field. Then you can calculate your force on this right side segment is like right up, right? And then you can see that from the symmetry, they're actually what the same in like, outer direction of this circle, but like they're both pulling it up, right? So the net force will be what? It will pull it up. So DFL plus DFR is going to be net force. The reason I'm using D is because I'm thinking of that small segment, right, of left side and right side, but you can keep doing it for around all the loop. So this one is along Z direction. Okay, it's toward plus direction. All right, and then let's write down equation. So the when you have a magnetic dipole moment in the B field, it's a potential energy. You can write it as minus its inner product. And then you will see that our, like, the picture, right? Our force picture up there is going to be the same as this mathematical description. So force is going to be minus gradient of UM magnetic potential energy. So you cancel out minus signs and mu B, okay? And then we're assuming a little bit here. So we're assuming some sort of a system that the B field, magnetic field, is X and Y components are so small compared to Z, so we'll kind of ignore it here, okay? They're zero. And then your inner product, you will only have Z component. And then mu Z is just for a given dipole, right? So it's not really a Z dependent thing. So you take it out. Okay. So this is going to be the force direction, or FZ component. And then the picture we have used is mu z is up, right? The way I described the circle is right-hand rule is pointing up. And then z vector is pointing up. It's a plus, but and it's getting stronger. So it's a z derivative is also bigger than 0. You can see that this equation is working, right? It's giving you the correct force direction. All right, and then let's look at this one. The picture used for Stern-Gala experiment. This one, it's similar to what I draw up there, but the difference is the P field is pointing down, right? So it's negative, basically. But it's the same in a way that it's a tensor up there, but it's pointing down, so it's going to give us the different sign. So in Stern-Gala experiment, one sec. This one is negative in this case, okay? So spin up case is representing something like up there, okay? Right-hand rule, I'll call that spin up. SZ is plus, then it's going to have, one second, let's see. Sorry, I just assume SZ is a plus, then it's an electron. So that magnetic dipole moment is minus, then FZ is up, okay? So this is going up because it's pushing up, spin down. SZ itself is negative, mu Z is positive, FZ is going down, okay, spin down. Then you will end up having this picture. I'll repeat the picture you saw again here. In up-down experiment result you'll get here. And then this result was showing that spin in Z direction are quantized. They're quantized, okay. It's like islands, there's nothing in the middle. It's not a continuous spread. And the reason why this is becoming an island, it's straightforward, but let's just, for completeness, let me just write down the experiments. You can just interpret it classically. X is given here, and then you have N here, S here. Then you have a magnetic field, and then Vx. With the Vx, the silver atom is coming in. And then if it's feeling force, right? It's a horizontal for the velocity will not change, right? Because there's no force in X and Y direction. So it'll just push up. So it's going to have this motion, right? And after it gets out of the magnetic direction, it's going to continue to have this straight line. And then opposite will happen for the other spin, right? So this is the velocity vector of spin up. This is a velocity vector of spin down. Okay, after passing through the magnet, let me call the length of the magnet as L. And then you can analyze this with the usual vector analysis Vx, Vz. Vx Vz. Okay. So the amount of delta T through the magnet section is going to be L over Vx, right? That's how long you are feeling this force through this, like passing through this magnet. And then the amount of acceleration along z direction, you can calculate, right? Fc over m, F equals ma. So Vz is basically Az times delta t, right? That's the velocity you will gain after passing through this magnet. And then that is Fc over m times L over Vx, okay? And then that is going to be the same as 2 mu b. Okay. S over h bar. That's a spin magnetic dipole moment. L over m Vx. So this equation is basically showing Stangella experiment, the result, okay, Vz. So in this equation, what we're measuring is, so we can measure Vz, okay, in this experiment, Vz, and you can control Vx and measure, okay, Vx you can, and then we know this one already. This is something you can design, is a constant. As a result, you can actually quantitatively measure the one in the parenthesis. So if you do so, what you'll get is you will get plus minus half. That's the electron spin. Okay, so that's why electron is called a spin half particle. Let me let me just use this way. H bar over half. So electron spin one half particle. Of course, there's a H bar, but it's always there. So you just ignore it and just like, call spin half. Okay, that's pretty much everything about Stangella experiment. That's how they found electron spin is a spin half. Okay, you have these two islands, and then these things are actually in a careful physics experiment, all measurable. Okay, you can actually measure S. Let's move on to this picture. I already showed you this. What's this one, right? So we will discuss this most interesting part of the Stangella experiment with the mathematical description. So this one is representing, once you filter out the spin up and then you put it again to the same box, you will only get spin up, right? So which means that there's no overlap between spin up and spin down quantum states. So it's they're orthogonal. You can see it from the experiment. Okay, sorry, this way. And then spin Z, okay, then you can think of it as okay, they can be probably used as the basis for the electron spin Hilbert space. So starting from here, let's work on spin's mathematical framework. So be careful when we're talking about spin's mathematical framework, we don't think about any other degree of freedom, okay? So of course, electron will have some electron spin, right? Electron itself will have orbital degree of freedom, and it can have many others. But well, we're gonna ignore it for a while, okay? We ignore it, only focus on spin. So it makes things very simple. So disregarding all the others degree of freedom, all the other degrees of freedom, spin quantum state can be described by the basis. Very simple. Spin up state and spin down state, it's their basis. It's finite. It's only two dimension. So any quantum state in terms of spin, this one arbitrary quantum state is basically expressed as this one. And then of course they need to be normalized as usual. So in matrix representation, we already have learned this. Let's repeat. You can assign as this one is 1, 0. This one is 0, 1. Okay. So spin, so as I've just mentioned in the Stern-Gerlach experiment, actually electron spin angular momentum, right? The S is actually what you can measure, right? What you can measure from Stern-Gerlach experiment, you can get what S is, right? So it is a physical observable, so there is going to be a Hermitian operator for it, right? Let me write it down. Spin angular momentum S is a physical observable. Therefore, it has corresponding Hermitian operator. Okay, so that operator, let's say that's SV operator, right? And then for spin up operator, what is the spin we get? We already wrote in the previous slide here, right? Spin up plus h bar over 2, spin down minus h bar over 2. So if you apply that operator to its spin eigenstate, you'll get eigenvalue equation with the eigenvalue here showing up here as a z applied to spin down quantum state minus h bar over spin down here. So SZ is going to be a 2 by 2 matrix, right? Let's find what it is. So SZ is going to become some A, B, C, D, and one sec. Why is it going? A, B, C, D are they are in complex number, okay? They are all complex numbers. We allow that to happen. So just do one by one. Actually, we don't need to go through all this calculation, but let's just, for completeness, let's just do it. A, B, C, D, you apply to 1, 0. It's going to be A and C. It's h bar over 2, 0, right? You do the same thing to spin down. A, B, C, D, 1, 0, B, D, 0 minus h bar over 2, right? So as a z operator, we already have found h bar over 2. 1 second, h bar over 2, I'll take it out. H bar over 2, 1, 0, 0 minus 1. Okay, right. So let's just do the sanity check. Of course, it should work. We apply this. You'll get this matrix, and then going back to bracket notation, this, as expected, apply to spin down. It's it's all as expected, and it's a very simple algebra, but it's showing, giving you all the essence of the quantum mechanics. So it's a spin is a very fun object to work with because it has, it's very, very easy. Okay, math, like your hand calculation is already simple, but it has all the gist of quantum mechanics. All right, and then so far it was very simple. And then z-axis, this is Sangella experiment. And as we have seen in the last time, natural question rises, right? Okay, there are other dimensions, x and y. How can you express spin operator along those directions? That's more interesting question. And that needs to be, and then the description of Sx and Sy operator, they need to explain the experimental result, right? They need to be configured in a way that it explains all the experimental results I've talked about last time. Okay, so to get there, right? To get there, we actually have to detour a little bit, because since we don't have much clue. So what I'm going to do is that we study angular momentum operator first, and then we learn from it, then apply it to spin, because they're similar, right? So as a reminder, let me show you the picture here. We have seen this picture last time, orbit and spin, right? They are similar, quite similar in the sense that they're both responsible for producing magnetic dipole moment for the charged particle. And then the difference between the Earth and Sun, like the Earth's movement and the electron, is that electron is actually not really spinning. Okay, it's as if it's spinning, but it's not really spinning. But Earth spinning really spins. So let's study orbital angular momentum. What's going on there? So we'll have a short visit to orbital angular momentum. Okay, so electron can produce magnetic dipole moment by both by both orbital and spin angular momentum. So the orbital angular momentum, right? Actually, you can, what is that? You can actually learn from classical mechanics and then start from there, and you will have a lot of clues. So let's do it together. So classically, L, so you probably have done this calculation quite a bit. It's R cross P, right? So your position and then momentum vector, outer product, you get L, right? So L is defined as R cross P, okay? And then, so I'm working on the classical physics, okay? And we're just reviewing classical angular momentum. So looking at the left-hand side expression, you can calculate all of this. And then each component, you can call it Lx, Ly, Lz. So in quantum mechanics, okay, so actually you already know these XYZ operator in quantum mechanics and PX, PIPZ operator in quantum mechanics, right? So you can actually plug in and then see if it works. So in quantum mechanics, Lx, Y, PZ, C, PY. Okay, you know what they are, right? We already have learned. Moment was a position and momentum operator in quantum mechanics. So it is natural to expect this also should work, right? Because quantum mechanics, when you make it more and more classical, it actually should match the classical results. So you expect this should work. This is angular momentum operator. And we learned the commutation relationship between the position and momentum operator. Let me write it down. You already have learned this. In the same direction, X and P, they don't commute, right? They're the uncertainty principle, they don't commute, but actually it doesn't matter if you have this orthogonal direction, right? They can commute, and X and Y also can commute. Momentum in different direction all commute, right? Okay. So using this fact, what we're going to do is we want to calculate the commutation relationship between Lx, Ly, Lz. All right. So when you carry out the calculation, you just need to use the commutation between position and momentum operators. So we will calculate Lx, Ly, which is defined as Lx, Ly minus Ly, Lx. All right. So it's actually an very interesting question. Lx, Ly, when you make the calculate the commutation, right? Is it going to be zero or not, right? That's an important question because we just saw that Px, Py are okay, they're zero, right? You can measure Px and Px very correctly, Py very correctly at the same time. It's a linear momentum, you can do it. This is an angular momentum, X and Y, okay? So if it's zero, it means that you can measure Lx and Ly simultaneously very accurately, right? But if not, there is this like fundamental problem of what is the uncertainty principle, right? They're conjugate pairs. If it's not zero, let's see what we get here. Lx, Ly. It's going to be a tedious calculation. Py pz minus z py. And then Ly is zpx xpz minus z px minus xpz ypz minus zpy. So all the algebra here is very simple, but one thing you need to be careful, don't swap their orders randomly, okay? You have to work with the commutation relationship. And then you can just do workout one by one. Okay, let me just work out one by one. One second. So I can do this. So let me take a pxy here and then in parentheses pxy, pxy, p. Okay, this term is corresponding to the first product. And then let me continue this. And then another one that has pxy, you can have pz, py, sorry, zpz. It's coming from this combination. Okay, let me just continue this calculation. Then there will be xy pz square. So I'm swapping their orders a little bit, but keep in mind that I'm only doing that when I can use that commutation relationship of 0, okay? Then you can swap orders. And there will be xy pz square. So this one will cancel out. Minus px py z square plus px py z square. It's also canceling out. Plus x py z pz minus pz z. Okay, so to wrap up, right? These guys are all canceling out. You have this one left. So that's going to be pxy. And then that equation itself is a commutation relationship, right? Pz z plus xpy z pz. So ZPZ, what was that? So ZPZ is going to be IH bar, right? So IH bar minus XPY, so XPY minus PXY. And then XPY minus PXY, actually, according to our definition here, is, what is that? It's this one. It's actually it's LZ. It's LZ, so it becomes very simple. Okay, it's actually not 0. You cannot swap their orders randomly. Okay, commutation is non-zero, actually giving you another operator, IH bar LZ. And then you can do this for other pairs because there are 3 LX, LY, LZ, so there will be 3 types of pairs. you have Ly, Lz, they're going to be IH bar Lx, Lz, and Lx. You can do the same calculation and you get this equation, okay? They're kind of rotating to each other's position, Lx, X, Y, Z. So the orbital angular momentum L has a really, really interesting commutation relationship, right? They have they're not commuting, and then as a result, their result is another operator that wasn't used on the left-hand side, right? So you get that, and then okay, so we actually have found a very interesting structure of angular momentum, orbital angular momentum, and then we were actually just now studying spin angular momentum. And although spin angular momentum, you cannot actually have this kind of derivation, sort of derivation, right? Because spin is just like a dot spinning. So you cannot really think about R cross P like picture. However, we will assume something here. Okay, this is kind of a postulate. You assume that it's going to work. So what we're going to do is that we'll assume that this works for spin as well. So and then justification of this kind of assumption or postulate, right, is always what? Experimental verification. Okay. If you model something with a math, and then that is predicting what's observable in the experiment, then we accept it. Okay, that's how your thought process should work. That's how science works. So back to spin angular momentum. We will postulate, okay, we'll assume commutation, the same commutation relationship works. So I'll just switch L to X, okay? Sx, Sy, IH bar Sz, Syz, IH bar Sx, Sz, Sx, IH bar Sy. So it turns out that it works. Verified by experiment. Okay, so commutation relationship works. So using that clue, we'll figure out Sx and Sy. So using that clue, we can figure out so such Sx and Sy are, well, I'm not going to derive those. Well, there are many ways to derive that, but many ways to figure this out. But let me just throw you the answer, and then it is not a unique answer, but it's a typical choice, okay? It's a canonical choice of spin X operator and Sy operator. And they are not unique, but they are the solutions. They work. It's not the only solution, but it works. Okay, so we will check what we just said, the important commutation relationship. It's all about just the math calculation. Okay, so it's a piece of cake calculating this plus I 0 0 minus I, right? Minus 0, sorry, minus I. 2I 0 0 minus 2I. Okay. So you are allowed to write it as take out I, get rid of 2, 0, 1, 0, 0 minus 1. You can write it as IH bar separately, H bar over 2, 1, 0, 0 minus 1, which is IH bar as the operator. Okay, we confirmed it works. So it is a working solution for at least for this commutation relationship, but you can check all the other two, right? And then of course it's going to work. So I just gave you confirmation. And then what you can introduce here is that, well, maybe you can think that matrix looks like whatever is in parentheses, like it's nice to have like one, right? One or I. And but there are these H bar over 2 is always there. So you can simplify like this. You take out that H bar over 2 part outside, and then you only work with these simple numbers. And then that sigma x is called a Pauli matrix. So sigma x 0, 1, 1, 0. Okay, it's much more simpler shape because you take out H bar over 2. The same for sy sigma matrix sz H bar over 2 sigma matrix sigma y 0 minus I plus I 0 sigma z 0, 1, 1 minus 1. So these are, as collectively, the three of them, Pauli matrices. Okay, Pauli matrix are introduced. Okay, so we now have the matrix for S spin X, Y, Z direction, okay? So in two-dimensional Hilbert space. And then we'll figure out eigenstate of Sx and Sy. Okay, this will give us a lot of information. And then it'll explain why Stern-Gala experiment is giving that result. And it's counterintuitive. It's not something you can expect from the classical picture. All right. Classical picture is just a magnet is pointing this way, this way, this way. All right. That's Z eigenstate X, Y, right? And then you feel like, well, there is no overlap, but actually you have. So let's see. You apply this to an eigenstate. I'm still using SZ basis, okay? The whole matrix, you always remember, I'm using what basis? I'm using Z basis, spin Z basis, okay? So in spin Z basis, Sx and Sy, eigenstate is what? That's our goal, to figure that out. And eigenvalue as well. It's an eigenvalue problem. Okay. Again, the problem is figuring this out together, right? Lambda and C on C2 all together we figure out. So the typical linear algebra approach, we'll take it here. We know Sx is what? It's this one. Something wrong with my iPad, sorry. Instead of writing this, the typical linear algebra approach, you put identity matrix here, C1, C2. Then you can convert this into this equation. But it needs to be 0. I just move the eigenvalue problem, the lambda right-hand side into left left-hand side, and then you make it, you rearrange the problem, and then you have to avoid the trivial answer of 0, 0, your determinant needs to be 0 in this case. So which is this one. So lambda value we already have found, plus minus h bar over 2. Okay. Spin, the magnitude itself is still not changing, right? Plus minus h bar over 2. So now our goal is to find out eigenvalue. It's a very typical process of finding out eigenvalue and eigenvector, right? So we just do this. So you just need to figure out C1 and C2 is what in this case, right? In this case, the simple solution will be they're equal. C1, C2 are equal, then it'll satisfy that, right? If you just do the calculation. C1, C2, they have to be equal. So to get exact number, let's do normalization. C1 square plus C2 square has to be 1. So you have a conclusion that this should always work, right? It's always true. And then we choose, okay? C1, C2 can be actually any number satisfying that equation, but let's make things simple. Let's choose to a specific solution for now. C1, C2. So we have this simple solution. And then in general, you can also put some global phase like this. So this kind of expression is called a global phase. Okay, global phase. All right, let's finish. Let's just let me mention one thing. What is that? That's a superposition of spin up and down. Okay. X spin eigenstate is a superposition of a Z spin up and Z spin down. That's an interesting part of the spin object. And that's explaining Stern-Gelag experiment results in the slide we used last week. Okay, let's finish here.